This is the Building Automation Monthly Podcast with Phil Zito, episode 170. Hey folks, Phil Zito here, and welcome to episode 170 of the Building Automation Monthly Podcast. And in this episode, we will be wrapping up our 5-part series on controlling HVAC systems with your building automation system. So if you haven't listened to our past 4 episodes, I really encourage you to. They have been some of, in my opinion, our best, most impactful episodes throughout the entire podcast, because HVAC is a topic that so many building automation professionals struggle with, and it's the primary thing that we control with our building automation systems. So I really encourage you to go back and listen to episodes 166, 67, 168, and 169, which can be found at buildingautomationmonthly.com/ whatever the episode number is. So 166 would be /166. This week's episode is brought to you by our Control Sequence Fundamentals course. Now, I've been talking to you about this course for the past 5 episodes. This course is the one and only course that will teach you exactly what you need to know about controlling HVAC systems with your building automation system. So this course is going to walk you through from space control all the way to complex central utility plants and everything in between. We're going to go through sequences of operations. We're going to pull out all the process variables and set points. We're going to talk about all of the logic flow. We're going to look at these sequences and really look at all of the theory as well as the practical application of how these HVAC systems work. So you can find out more about that by going to buildingautomationmonthly.com /170, scrolling down to the HVAC, or rather the Control Sequence Fundamentals logo, and clicking on that logo, and it will allow you to watch a sample video, read some student testimonials, as well as look at the course workbook. With that being said, let's dive into this week's episode. So in this episode, we are going to be talking about pumping and piping. So we're going to look at the different types of pumping. We're going to talk about the different types of piping. We're going to talk about primary loops, secondary loops. We're going to talk about decoupled loops. We're going to talk about staging scenarios associated with decoupled loops, and probably a couple other topics as well. Now, this episode will most likely be shorter than our past 4 episodes because we're just covering piping and pumping. However, realize that piping and pumping are like the heart and veins of a building. So if you think about HVAC equipment being the muscles, and if you think of the BAS being the brain, while the pumps and the pipes are the circulatory system that allow the control mediums like hot water or chilled water to circulate from the central plant throughout the building to the individual pieces of equipment. So without them, we would not be able to heat and cool our buildings at a large scale efficiently. So how do they work? In order to understand piping and pumping, we've really got to understand flow as it's seen from the perspective of piping and pumping. So the first concept we need to cover is this concept called T's law. Now, I didn't know this for the longest time in my career, and knowing this would have avoided a lot of issues. And what it is that whatever goes in the openings of a T must come out the remaining openings. So if you're wondering what a T is, basically think of your primary secondary loop, right? And think of how you can have kind of where it tees off, where it taps off. The piping does. So normally what will happen is you will have either a decoupler or you will have a actual valve. A mixing valve is often what it's called. and that valve will restrict the flow of the water. Now, what's going to happen is because that water flow is restricted, it is now going to divert to that secondary loop. And so let's say it's closing off. Let's say we have 100 GPM. And that valve is closing off to the point where only 35 GPM can get through. Then on the secondary side, you would see 65 GPM going through the secondary loop and 35 GPM going through the primary loop to equal still 100 GPM. Now, that is how we go and mix water into an actual secondary loop. So what happens then is that by allowing this water in, we're able to have a primary loop that circulates and then let water into the secondary loop as required. And this keeps us from having to run pumping power throughout the building to distribute this cooling water or heating water, and it also allows us to keep this cooling and heating water in a more localized loop so that we don't have heat gain or heat loss. All right. And what can also happen, right? What can also happen is that because of T's law, you can have this concept called an overactive pump. And that's where you have pumps that are oversized on the secondary, and those actually start drawing water back from the return into the secondary loop. And this is often why it's very important to understand how we control our pumps, especially if for some reason we have an oversized secondary pump and we're trying to control that. We can't have that driving more than the primary pump because we will start to pull water from that primary loop rather than it returning. So we can run into issues there. And that is not good as well. So whenever we look at temperature control and we start to think about mixing valves, right? And a mixing valve, as I said, is to mix the primary and secondary loops. What we often will use is this equation that will help us calculate the mix temperature, which is GPM1 times temp1, so that would be your primary loop, plus GPM2 times temp2, and that's going to be our mix temperature. And so that is going to tell us what the resulting temperature is when we mix our primary and secondary flows. But it also is going to potentially point to an issue. And that is, if you have mixed matched flows, then you're going to have an issue potentially where you are not hitting the transfer across your coil. And so what that means, if you think about our approach on a coil, right? So the entering temperature and leaving temperature, we typically want to have a 10 to 12 degree approach, meaning we will drop 10 degrees across our coil, and that allows us to really condition the air. But when we don't have a mixing valve and we have mix-matched flows, as I described with oversized pumps, we can actually get to a point where we can't maintain our secondary supply temperature because we are drawing heated water from that secondary return. I told you guys this is going to be pretty complicated. And in our control sequences course, we actually have diagrams that go through this, which make it a little bit easier to understand. But the thing is that what's happening, right? You've got this primary loop and it's letting water into the secondary loop. And this secondary loop is sending the water through a cooling coil, which is then warming the water up. And now, so the water's coming in and it's leaving at 55. But if you have an oversized pump, it's getting drawn right back in across a decoupler into that secondary loop, and then you start to have where your secondary loop warms up. That's why we put in mixing valves, and that's also why we put in VFDs on our secondary pumps, so that we can control pressure and we can also control flow into the secondary loop so we don't have this issue. It's really important that you understand this, especially if you're dealing with decouplers or variable speed drives on the secondary and you're not properly controlling your mixing valve, because you can get into that issue. Now also, right, so you have these VFDs now and you're handling that GPM issue. So you're no longer having a drawl of GPM that is pulling water back into that secondary loop. It's overpowering the primary loop. But now we have a different issue. We can actually go with that secondary, or with that mixing valve, we can actually make an issue where we have starving coils because we're not giving them enough flow. And so this is where VFDs come in. And this is something that's really an important difference. And it's something that, once again, I was really good on air side. I was really good on the hydronic side, but the pumping and piping, I just wasn't 100% on early in my career. And so I thought, VFDs, we could just control pressure to overcome any pressure issues that have to do with going up a building, right? Because there's pressure as you try to push water up. But in actuality, that is part of it. But one of the biggest reasons we use VFDs is because when we use a mixing valve, we can go and starve our secondary loop. And what will happen is the VFD will help us to go and overcome this kind of low DeltaT syndrome. And what low DeltaT is when the actual temperature between two, or the delta between two temperatures, the difference between two temperatures, when it is too low. And basically what happens is you're not transferring BTUs. So what's going on is that we want to make sure we're drawing enough from the primary and we are still maintaining that 10-degree differential. And I'm talking chilled water side here. Obviously, boilers are going to be a little bit different as far as their temperature delta between primary and secondary. So I'm mainly focusing on chilled water here. It's basically the same principle, just bigger deltas. But with that being said, DeltaT can actually go and cause issues where we are not getting a good exchange across our coil. You can actually be sitting there and not pulling enough out of the primary. There's multiple different things that can happen, but primarily when you hear low DeltaT syndrome, and you go and you measure your pre and post coil temperatures, you look at the temperature gauges on the piping. This is another reason why on large air handlers, I recommend things like the Belimo energy valve, where you actually have temperature sensors and flow sensors, and you can really get a good idea on coil performance, especially for critical airside systems. But regardless, you measure your GPM, you measure your temperature, and if you see that, hey, I've got 48 coming in and 50 going out, then that's an issue, right? Or 45 going in and 47 coming. There's a variety of different ways that this would show itself. It's just important to realize that that means you most likely have a flow issue, especially if the incoming temperature is accurate. So, assuming that your systems are properly balanced, mixing valves and variable speed pumps are going to enable you to maintain a pressure drop, which is another concept we'll talk about in just a second, and therefore an adequate flow rate to maintain your design DeltaT, right? Because assuming you have the right temperature coming from your primary loop, so you're not in weird design days where your primary loop can't keep up, then your mixing valves should be letting the right temperature come in. So your mixing valves are controlling off of loop temperature, and your variable speed pumps are controlling off of a pressure setting, typically at the end of the piping run, so that you're not starving any valves, because the valves will naturally close themselves off at the beginning of the run, and they will start to open up much more at the end of the run. And what that means is that you want your pressure sensor typically at the end of the run. That way you can have an accurate representation of pressure drop. Now, this isn't always the case, but that's usually how it's designed. Now, there's another concept that I talked about, and that's pressure drop. And pressure drop is the difference between the entering and leaving pressure. So as you send water through a coil, you're going to lose some pressurization because your pressure is going to drop as that water is pushed through the coil, because it's naturally going to contract going through the coil. It's going to get basically resistance as it starts to go through all of the elbows, and that resistance is then going to cause a pressure drop. All right, so what you're doing then with your speed pumps is you're overcoming that pressure drop. And that is the fundamentals, right? Kind of the fundamentals of controlling pumping and piping. Now we're going to go a lot deeper into primary secondaries. We're going to go a lot deeper into decouplers in just a second, but I want to talk about one last thing, which is DeltaT at full load conditions. So you have a coil and it's designed with a 10-degree delta, right? But due to it being plugged or whatever, you're only getting an 8-degree delta. And so this means running at full load, we are only using 80% of its load. And this perceived lack of load is going to cause the secondary pumps to run harder. We're going to turn up, potentially going and staging additional chillers. And you're going to see that this is going to look like DeltaT, but you're at full load and you're at design. And so how is it DeltaT? How is it a low DeltaT syndrome? It's actually not. This is usually a sign of poor maintenance on the actual pumping and piping system itself. So you want to be cognizant of that as you go and troubleshoot systems, especially this summer when some of you, depending on where you're at, are going to be running into systems that are fully loaded. If it is a older building, this is something I would definitely be cognizant of. That and balancing valves. I recall I was troubleshooting a central plant. This is back in Texas for a church, and churches are massive in Texas. I think this church had like 20,000, 30,000 people. And it had 3 centrifugal chillers and a smaller centrifugal chiller. And it had a decoupler. And we were trying to figure out why the secondary loop was just out of control. And what it ended up being, we went into the central utility plant. And you could hear that one of the pumps was deadheading. Someone had bumped one of the multi-purpose valves. And so that's a valve that serves as a strainer, as a balancing valve, etc. And what happened is they bumped it and partially closed it, and that actually was constricting the flow coming out of one of the secondary pumps. Alrighty, so primary pumps. So the purpose of these, obviously, is to provide water flow and to go and allow flow not only through the primary loop, but also through the cooling or heating system itself. There's 2 typical types of pump control for primary pumps. They are normally associated with a piece of equipment if they are in parallel. And if they're in series, they will normally go and be distributed. At least I think I'm saying that right. I'm trying to visualize parallel and series in my head right now, early in the morning, and I may have mixed that up. But the important point is that some of them are constant volume, some of them are variable volume. Now, what's going on with variable volume pumps, right, is that you are going to vary the flow based on the demands of that primary loop. So you're going to go and increase flow as needed. But with a constant volume pump, it's going to be sized directly to that chiller, okay? So the big difference in controlling this is that with just static, constant volume pumps, you are not going to be able to do much with your GPM, and you're going to really have to focus in on, if you have a secondary loop, on getting that secondary loop control tight. Now, if you do have variable flow on a primary loop, and you'll see this in a couple different scenarios, you want to focus in on that as well, because you don't want the secondary and the primary loop fighting one another. All right, so primary secondary loop control. So why do we have secondary loops? Secondary loops exist to shield heating and cooling systems from low or high temperature water. You don't want to introduce some crazy temperatures into a cooling or heating system. That can be bad. It also is going to contain it within a smaller primary loop and then mix it into the larger secondary loop as necessary. And we talked about why that's important, because we don't want to be piping this conditioned water all throughout a building using all that pumping power if it's not required. And so how do we do that? Well, like I said, we use mixing valves and VFDs. So the mixing valve is a valve that is typically 0 to 10, 4 to 20 signal, and it is controlling off of the differential pressure and set point. So you've got a PID loop that has a pressure and set point going into it. It's a fast acting loop, just like with an airside system, and you are going to be driving that valve accordingly. And then sometimes, or I'm sorry, I totally just mixed that up. I don't know why I said you're going to be driving a valve off of differential pressure and set point. I meant to say you're going to be driving it off of temperature and set point into a medium speed loop, because typically you're going to have anywhere from 10 degree on the chilled water side, and you're going to have 20 degrees on the hot water side. Man, I tell you, do not do podcasts without drinking coffee beforehand, because, anyways. Now, the pumps themselves are going to control off of pressure and or GPM. So you're either going to control pressure or GPM. You tend to see GPM as the control variable more in a decoupled loop. Because you can have reverse flow, and you're going to be looking at your GPM of your secondary, and you want it greater than the GPM of the primary to draw water into the secondary, because it's a decoupler. There's no mixing valve. It's just a straight pipe. Now, with the mixing valve, you're going to typically be controlling off of differential pressure and set point. As I said, the pressure sensor is typically at the end of the run, and you're going to be going and maintaining that pressure drop. So you're going to want to make sure that you're providing adequate pressure so that you have the optimal flow to get the proper exchange through the coil on the different airside systems. All right, making sense so far? Hopefully it is. I know this is one that's frustrating to me to present in a podcast format, to be completely honest, because so far everything we've talked about in this series, I could go and just describe and it would make sense. But this is something that I really feel would be better if there's some diagrams. I think what I'll do is I'll pull out a couple diagrams and post them actually on the episode at buildingautomationmonthly.com/170. That way you can go and refer back to them. So there will be a diagram about DeltaT. There will be a diagram about the decoupler, and there will be a diagram about a overactive secondary pump. I think I'll put those three on there. I think that will really help. All right, so at this point, we've talked about piping, pumping, T's law, overactive pumps. We've talked about pressure drop. We've talked about decouplers a lot, but we haven't really went through them too much. So decouplers is basically, instead of a mixing valve, you use this piece of pipe called a decoupler, and you use a variable volume secondary pump to modulate flow through the secondary pump. And what it is it's a pipe segment, right? And it bypasses the secondary loop. This is why we talked about T's law earlier in this podcast. And what's going on here is that each chiller will stage on with a primary GPM pump, right? So it's going to have a pump, and let's just use round numbers here. Let's say there's 2 chillers and they have 200 GPM, and they turn themselves on, and we've got 200 GPM on the primary side. Now, in order to pull water through that decoupler, we're going to have to overcome that 200 GPM, because naturally it's just going to go and push right through. And so what's going to happen, in order to pull water into that secondary loop, we're going to have more water than the primary loop. And when that happens, we are going to be drawing water into the secondary loop out of the primary. Now, When the valves start to close on that secondary loop, the pressure is going to start to have to be regulated, and the pump is going to start to slow down, and that is going to cause a drop in GPM, right? And so the GPM on the secondary loop is now going to be less than the primary loop. And at a certain point, whatever that is, the chillers will then start to stage down because their GPM will be much higher than the GPM of the secondary loop. So that's how a decoupled loop works at a high level, is you stage chillers on when their primary GPM is, or the primary GPM loop, the GPM of the primary loop, my gosh, cannot speak this morning, is lower than the secondary loop. Then you're going to start to stage chillers on. And then when the secondary loop is much lower for GPM than the primary loop, you're going to start to stage your primary loop down. Okay? Did I say that right? Yes, I think so. This is why you need a diagram for this. Oh my gosh, because I'm visualizing primary pumps and chillers, and I'm also visualizing secondary side at the exact same time, and I'm trying to do this equation in my head of, okay, yeah, so the primary flow is higher than the secondary, so I want to turn down my chillers. Yep, that's right. And then when the secondary is higher than the primary, I want to turn on my chillers because of I'm just going to be drawing water back through the decoupler instead of letting it flow through that primary loop. It's a confusing concept when you're listening to it from an audio perspective, but if you draw it out, it's in my opinion, when you get the timing right of the stage up and stage down and you get your loops tuned properly, this is actually one of the easier ones to control, decouplers. I actually like working with them versus going and using a mixing valve, because there's, in my opinion, less variables. Now, granted, it's a little more expensive because of all the flow sensors and things like that, but it is what it is. So there you have it, a early morning podcast episode on pumping and piping. I'm sure that in some ways this episode confused you all. I just don't know of any other way to communicate this clearer. It's a confusing concept, but it's also not when you start to work on it. So that's kind of the thing with pumping and piping. As long as you realize it's a circulatory system for the conditioned water coming out of our hydronic systems, right? So it is essentially the heart, the pumps are the heart, and the piping is the arteries. And then your secondary loops are kind of like your veins and capillaries, right? So going back to our basic anatomy. And when you understand that, you start to kind of understand how pumping and piping works. It's not too terribly complicated. However, with that being said, if you do have any questions, I'd really encourage you to ask them at buildingautomationmonthly.com/170. Quite honestly, I'm kind of happy to be getting out of this HVAC topic. I'm feeling the itch to be talking about technology. So I think next week's episode is going to be something to do with technology. Throughout the summer, the episodes are typically going to be a day or two late. We're not typically going to be hitting Monday, just due to all that's going on both in my personal life as well as we've got a course that we are producing right now for BAS project management, and so that takes a lot of my focus as well. So with that being said, thanks so much for being here. Appreciate you all as always. Thanks for all the reviews on iTunes. Thanks for all the shares. And I also want to say, if you have any questions, there's several of you who reach out to me. I really encourage you to do so. I like answering your questions. So thanks a ton for listening, and I will see you all, or talk to you all, on the next episode. Take care.